Hi, so in this video you can clearly see I'm going to talk about forces, and this is on paper 2, which is section 4.5. So you only need to cover this material when you are doing paper 2. Okay, so the material we need to know about for forces, which you can see on this specification is 4.5, is forces and their interactions, which is scalar and vector quantities, contact and non-contact forces, the effects of gravity, the equation for gravity involving weight and mass, resultant forces and being able to work out the components and how to resolve the components into vector diagrams. We need to be able to do work done and use the equation for work done, which is force times distance or displacement. We need to know about the effects of forces and elasticity, so on a spring, and how this affects things like elastic bands, etc., with stretching and compression. You need to be able to use the two equations for both elastic potential energy and force equals the spring constant times the extension. And you also need to know about the practical activity, which is a required practical. It's required practical 6, and that is the relationship between force and the extension of a spring, which is Hooke's law. Okay, so if we start on forces, the first thing is, what is a force? So a force is basically a push or a pull, and it's going to create movement. Now the movement it creates is always in the direction of the force, and this is from a resultant force. Now remember, a resultant force is the overall or sum of all the forces. So if we had a resultant force here of say 8 newtons, so we just draw that on there, say this force was 8 newtons, then this object is going to accelerate in the direction of this force. Remember, a force causes an object to accelerate, and it always accelerates in the direction of the resultant force. So the overall force is 8 newtons here. So what will the object do? It will accelerate in the direction of that force. Okay, so it's moving in that direction. Now there are two main types of forces that you need to know about. The first one is a contact force, and the second one is a non-contact force. So what do we mean by a contact force? Well, there are four main ones you need to learn about. Friction, which is basically when any particles in material rub against each other. So when we move the box on top of a table, the particles in the box are rubbing against the particles in the table, and there will be attraction between these particles, causing heating effect. Air resistance is the same, so as this person's moving down, you can see the particles in their body are getting hit by air particles, and this is obviously a contact force between two particles. Drag is the same, but in this case it's going to be in water. Now drag could also be air resistance, remember, but if you use the term drag, it will cover air resistance and also water resistance. So drag is when the water particles are resisting the motion of this swimmer, for example. The other contact force you need to be aware of is tension. So obviously you can see here we've got mg, which is basically the force, because the force or weight of an object is equal to the mass of an object times its gravity. So that's saying that this is applying a force, and that's applying tension in the string. So tension in a string is another example of a contact force, because you're putting a tension on the thread, the string, the elastic, a spring, etc. Okay, non-contact forces, generally the ones you need to know about, are to do with fields. So you can see that gravity, the electrostatic and magnetic are all non-contact forces, and they are non-contact forces because they provide fields. Now remember, if we were to draw a field around the Earth, then the field would look something like this, and objects are always pulled to the center of the Earth because they are pulled by this field. So if I had an object there, it would be drawn, or it would accelerate, let's remove that, in the direction of the field, so it gets pulled to the center. The same with charged particles. These particles also have a field, an electrostatic field around them, and they get pulled in the direction of the field. Poles are exactly the same. From north to south we would have a field, remember, around a bar magnet, okay, which would look something like that. So it would always get pulled from the north to the south pole. So remember that all these objects have fields, and it is the interaction with that field that causes a force. So the particles aren't specifically touching each other, the magnets aren't touching each other, but the fields are interacting, and that creates a force. So we either have a contact force, which is when particles interact and they touch each other, or we have non-contact forces such as gravity, the electrostatic or magnetic, and that is when fields interact with each other. Okay, so moving on to vectors. Okay, so you need to understand that a vector has both a magnitude and a direction. Okay, now a magnitude is just a number attached to the size of the force. So if I had, for example, 5 newtons, that would be its magnitude. If I give it an arrow, in this case we're going east, then it now becomes a vector because it has both a magnitude, which is the number, and a direction. So any vector has to have both a magnitude and a direction. Okay. Now, I talked about this before. If I just remove the ink from this slide, you can clearly see that I've put that a resultant force is the sum or total of all the forces. So if I had 5 newtons of force pushing up and I had 4 newtons of force pushing down, the overall force would be 1 newton up. That is the overall force of those two forces combined. Okay, so that is the sum of all the forces. So the resultant force would, in this case, remember, create acceleration, and the object always accelerates in the direction of the force. Okay, so I'm now going to talk about some vectors, just so we understand the effect of different forces and how it will combine, or how they combine to create a resultant force. So if I put some numbers on these forces, we start with this one. Say we give this a 10 Newton force, and obviously this force is lower, so I'm going to give this a 6 Newton force. Remember, the resultant force, because they are going in opposite directions, is going to be 10 minus 6, which is equal to 4 newtons. So that would be the resultant overall force. So that is the sum of those forces combined. Now, if the forces are going in the same direction, say this one's 8 newtons and again this is 6 newtons, then we're going to add them together. So 8 plus 6 is going to give us a resultant force of 14 newtons. And this makes sense. If two people push the object in the same direction, they're going to apply a greater force than two people who are pushing in opposite directions. Now, what about this one? Well, these arrows are obviously the same size. So again, I'll say these are 5 newtons, and we'll give this a force of, say, 8 newtons again. So what am I going to do this time? Well, because we have 3 arrows, it means we have 3 times 5. So we're going to do 5 times 3, which is equal to 15 newtons. And 15 newtons, this time minus our 8 newtons, is going to give us a resultant force of 7 newtons, and that's going to be up. So make sure you describe the direction. So that's going to be 7 newtons up, that'll be 14 newtons down, and that'll be 4 newtons down. So you can see these are the resultant forces. But what about if we have an object that has 3 forces on it? Well, the first thing is we're going to cancel out the first forces. So if this is 8 newtons, we'll say this is 6 newtons, then we're going to work out that force first. So what is 8 minus 6? Well, that's going to give us a resultant force of 2 newtons. So I'm going to redraw this diagram now, knowing that one force is going to go that way and one force is going down with an overall force of 2 newtons. Now let's imagine that this is 5 newtons. So we've got a force here of 5 newtons and a force here of 2 newtons. Now how do we work this out? Well, there's two ways. One way, you could measure this with a ruler. So there should be scale diagrams in your exam. So just to simplify this, imagine this is 5 centimeters, and therefore this force you would draw. Now we call this a tip to tail diagram. So we're going to put the tip of the next arrow, the next force, on the arrowhead here. So you can see that gives me my 2 Newton force there, like so. Okay, now when I've done that, if that was 5 centimeters representing 5 newtons, then that must be 2 centimeters up. So the scale is that 1 newton equals 1 centimeter. So 2 newtons is going to be 2 centimeters. Okay. Now, how do I work out my resultant force? Well, I show from the start of one to the end of the other. So from here, where I start, I'm going to draw a straight line to where I end up at. And the resultant force is this line. So if I measure this, and I measured it, and it equaled, say, 5.6 centimeters, then my overall resultant force would be equal to 5.6 newtons. Okay, and that would be in a direction that is at this angle. Okay, so I could measure this angle and say that angle was 20 degrees. It would be 20 degrees up from the horizontal. Okay, or from the vertical, you could say that it is 70 degrees down from the vertical, or 70 degrees to the east. Now, another way we could look at this is because we are creating, if I just go back to my original color, because we are creating a right angled triangle by having a 5 Newton here and by having a 2 Newton force there, as soon as I put my resultant force in, I now have a right angled triangle. So how could I work this out? Well, I could use Pythagoras, and we know that c squared is going to be equal to a squared plus b squared. So if this is a squared and if this is b squared, it doesn't really matter, then I know that 2 squared plus 5 squared, if I continue that up there, is equal to 4 plus 5 squared, which is 25. So therefore I know that c squared is equal to 29. So c must be equal to the square root of 29. And if we work that out, we would get our hypotenuse, which is the answer. And that would give me an exact number. Just like measuring this line would give me an exact number, I could do both. I could do a scale diagram, or I could use Pythagoras to calculate this resultant force. Okay? Okay, in this video we're going to do the final vector diagram, and this is a little bit more complicated, so we're going to have a look at this one in more detail. So we're going to start it on a new page, and as you can see there are 3 forces acting on the object this time. So we need to what we call resolve all the forces. We need to add them together and see what the overall resultant force is going to be. So we're going to say that this force here is 8 newtons. We're going to say this force here is 10 newtons, and we're going to say this force here is 5 newtons. Okay, so now we know the forces, we need to measure one of the lines, and they should all add up to give a scale. So if I measured this line and it represented 4 centimeters, then if 4 centimeters equals 8 newtons, 1 centimeter is equal to 2 newtons. So we now know what 1 centimeter is equal to, or what Newton would be equal to. 1 Newton would be equal to 0.5 centimeters. Okay, so now we know that, we can now move this onto a scale diagram. But before we do, we need to know the angles. So in your exam, you would need to measure the angles from the horizontal, and I'm going to tell you that this angle here is 25 degrees from the horizontal, and this angle here is 50 degrees from the horizontal. So we've got a force of 10 newtons, which is at 50 degrees, and we've got a force of 5 newtons, which is at 25 degrees. Okay, so how do we put these together? Well, we do the same thing as we've done with all the other diagrams. We do a tip to tail diagram, and that means we just add the vectors together. So we're going to start off with the 8 Newton vector. I'm going to draw a line down here. Now remember, that is 4 centimeters. So when you do this, it has to be exactly 4 centimeters, and that angle has to be 90 degrees. It's a right angle, it's straight down. Okay, so we know that that's 4 centimeters. How do we put the rest together? Well, we're going to then do a dotted line, and this must be at exactly horizontal. And from that point, we're going to put the 10 Newton line on. So at this exact place here, I'll just draw a nice circle there just to represent it. We're now going to do our 10 Newton line. Now remember, our 10 Newton line must be 5 centimeters long. So we're going to measure this 5 centimeters. But how do we know the angle? Well, we go back to our original diagram, and it's 50 degrees. So from there, we're going to draw a 5 centimeter line, and where that hits there, you know that is the end of this vector. that angle is 50 degrees because it's the same as the one here. So that is going to be 5 centimeters because 5 centimeters is equal to 10 newtons. We know that that 4 centimeters was equal to our 8 newtons. Now for the final one, because they're all going down, we add them together. So we're going to put that on there. Imagine that this is an exact point here. We're going to have a 5 Newton line. So from this point here, we know that that is going to be 2.5 centimeters long. So that's a 2.5 centimeter vector, and the angle is the same as that angle. It's at 25 degrees. Now if you do this accurately with a piece of paper, a protractor and a ruler, like I have done, I can give you what the exact value should be. So from here, we now are going to do our resultant. So from that point to this point, if you've done that properly, you will get a line that goes from there to there. And our resultant force or resultant vector is going to be equal to 10.5 centimeters. 10.5 centimeters, remember, using our scale, we need to multiply that by 2. So our resultant force is going to be equal to 21 newtons. Okay, but that's not it. Remember, a force has to have, for our resultant force, it has to have a magnitude and it has to have a direction. So the direction is from the horizontal. We're going to measure this angle. Now if you do this accurately, you will get an angle of 60 degrees. So you know that if you get 21 newtons of force and 60 degrees down from the horizontal position, you have done it correctly. Okay, so that's the exact values you should get for this vector diagram. Now moving on, we're going to look at a couple more. So we've got one here that we could do. So this one is 8 newtons. Up here we've got 6 newtons, so we just put those together, and again we would use our protractor and we would do a scale diagram from the tip here to there. And if you measure that angle correctly, you will get whatever resultant vector that is. So that will give you your resultant force. If we looked at this one, again, if I just change it to purple, so all we have to do again is we draw one arrow, which is 8 newtons. We measure that line and we put the tip of that one on the tail. So this time it's going to be down like that with the same angle as that 6 newtons. So we've got 6 newtons that way, 8 newtons that way, and our resultant force is from the start to the end again. So that is going to be from there to there. Okay? And whatever that resultant force is, you would measure the length of the line and you would measure the angle there. Now we're going to practice this more in the exam questions that supplement this video. So if you're still not understanding it, when I go through the specific exam questions, they should help you out with this particular topic. Okay, so moving on from this, we're going to talk about gravity. So gravity is the force that acts between two masses. So any two masses must have a gravitational attraction, no matter how small, whether they be electrons, protons, or planets, they all attract each other based on their mass. The greater the mass, the greater the force of gravity. Okay, so gravity acts from a single point, and this is called the center of mass. So if I had a particle and another particle, they would act from their center of mass, pulling each other from their center of mass. Now we drew a diagram of this before. We said that if you stand on the earth as a person, you will always be pulled towards the center. No matter where you are, if you stood there, you will still always be pulled towards the center of the earth. So gravity acts to the center of the mass, whether it be a huge planet or just a particle. It's the same thing. It's going to act towards the center. I'm just going to get rid of this ink and carry on. Okay, so here's a diagram of Newton, and we know that apples were said to have fallen from his tree, and this is how he came up with his idea of gravity. Okay, so gravity gives objects weight. Now, weight is a relationship between an object's mass. Now, remember, mass is just the particles anything is made of. So, particles, objects are made from. And it's so easy to make a misconception with the difference between weight and mass. The particles objects are made of will tell you that if you go into space, and you stand on the moon, if you were stood on the moon, you would weigh less than you would if you were stood on the Earth. Now remember, the reason for this is because the gravity on the moon is less. It's about 6 times less than it is on the Earth. So you would weigh 6 times less on the moon than you would on the Earth. The reason for that is because your mass would always be constant, because you are still made of the same particles, but the gravity is 6 times less. So if gravity is 6 times less, you would weigh 6 times less on the moon. Okay? Now, just to iron out a misconception, in space, you don't weigh nothing. There is gravity in space, so please don't ever say that in space you have no gravity and that's why you float. Okay? Because that is a misconception, and the reason that you float in space is because you are falling, not because you have no gravity. There is no place in the universe where there is no gravity. Okay, so moving on and talking about this equation, if weight is equal to mass times the gravitational field strength, so basically W is equal to m times g, W is a force. So the mass times the gravity gives you the force. Okay, so this is the force of an object. Now we'll carry this on. Okay, so I said W is equal to m times g. This relationship is directly proportional. So what does that mean? Well, it means that for W, if I increase m, so say W is equal to 100, and that's equal to 20 times 5. Okay, if I increase the mass, I must increase the weight by exactly the same amount. This is what a directly proportional relationship means. So say I increase this by 2 times, so 20 times 2 is 40, then 40 times 5 is going to give me 200. Can you see that increasing this number by 2 will increase this number by 2? They are directly proportional to each other. And a directly proportional relationship on a graph will always look like this. The sign for a directly proportional relationship is that weight is directly proportional, this is what this sign means, to the mass. Okay? So any calculation that is weight is equal to m times g, or that F is equal to m times A, any relationship like this is a directly proportional relationship, because increasing one of them will increase the other one. That's what directly proportional means. So make sure you're aware of that for your exam, because this is the type of mathematical question they might throw in to try and make sure you understand what that actually means. Okay, so moving on from that, we're going to have a look at work done. Now, work done is the energy transferred when you move an object. So you're going to move it a specific distance. So because it's energy transferred, it must be in joules. So work done is in joules. So I've just said that it's the energy transferred moving an object which has a force, and it depends on how far you move it in the direction of the force. So work done is equal to the force times the distance, and S, remember, is the distance, but it's called the displacement, and displacement is just the distance in a straight line, kind of as the crow flies. Okay, so how do we do this? Well, let's have a look at this box. We've just moved the box from this position to this position. So we could work out the work done by working out how many newtons this box has of force and how far we've moved the box. We could also look at moving the box up. So if I just rub out the ink from this slide, okay, let's do a little bit of maths so we make sure we understand it. If I've moved this box 1 meter, now remember the energy that we're using is by moving this box against friction. So it's the work done against friction. In this particular one, we're doing the work done against gravity. So it's against a force, okay? This is a contact force, this is a non-contact force. So work done is equal to force times distance. We'll give this box a force of 10 newtons, and we'll say that we've moved it 1 meter. That means the work done is equal to 10 joules. That means I've had to put 10 joules of energy in to move the box. and therefore that box must have transferred 10 joules of energy, and that's going to be into heating. So that's going to increase the thermal store. It's going to increase the thermal store. So we're transferring our energy from the kinetic store into the thermal store. We're going 10 joules kinetic into 10 joules of thermal energy. Well, what about this one? Well, the box is still the same force, okay, so it's still 10 newtons, and it's still the same equation. We'll say we've lifted it 2 meters this time. So what will we do? We'll do work done is equal to force times distance, and we know that the force is 10 and the distance this time is 2 meters. So the work done to lift this up against the gravitational field is going to be 20 joules. Okay, so where's the energy gone this time? Well, the 20 joules of kinetic energy moving it up has been transferred and stored is a gravitational store. This is a gravitational store of energy. So this box now has 20 joules of stored gravitational potential energy. And should we let go, that energy would then be released and the box would fall towards the earth and then transfer that energy as sound and heat. Okay, so moving on, let's do some calculations. Okay, so putting that into some context, we're going to do a couple of equations using what we've learnt. So we can use work done, we can use gravitational potential energy, we know the equation for weight as well. Okay, so here the first question is, what is the weight of the crate? So we know from our previous slides that weight is equal to the mass of an object times the gravity. Okay, now for this we're going to say that the gravity is 10. In the exam you will always be given the gravity, so make sure you read the question. It might be 9.8. Make sure you read the question. So if the mass is 1500 kilograms, we know that that is equal to 1500, and we multiply that by 10, and that is going to give us 15,000. And weight is a force, so it must be in newtons. Now the next question says, what is the upwards pull on the crate? Well, if we know that the downwards weight we've just worked out is 15,000 newtons. In the question it says it's been pulled at a steady speed. Now a steady speed means a constant speed, and that means no acceleration. If there is no acceleration, then we know the forces must be balanced. There is zero resultant force. The resultant force is equal to 0 newtons. So that means that if the force pushing down is 15,000, the force pushing up must be 15,000. So what is the upward pull? That must be 15,000 as well, because the forces are balanced. Okay, how much work is being done by P in raising the crate a height of 4 meters? Well, we just said that work done is equal to force times distance. The force is 15,000 and the distance is 4 meters. So 15,000 times 4 is going to give you 60,000. Now work done is the energy transferred. So that box, by being lifted 4 meters, has gained 60,000 joules of energy. It's gained 60,000 joules of gravitational potential energy. What is the gain in gravitational potential energy if we lifted it 4 meters? Well, we just said that it must be equal to 60,000. So what's this telling us? It's telling us that gravitational potential energy and work done are the same equation. Now, gravitational potential energy is equal to height times mass times gravity. So how do these interlink? Well, we know it's been moved 4 meters. The mass is from our original equation. It's 1500. And this is 10. Well, where did we get this from? Well, we did this before when we worked out the weight. It's 1500 times 10. So that force, remember, is equal to m times g. So these equations both mean the same thing. They will both give you exactly the same answer of 60,000 joules. So if you have the height times the mass times the g, you can work out the GPE, or if you have the force times the distance. Either one gives you the same number. Now for the last question, we need to work out the GPE if the crate is lifted 9 meters. So all we have to do is multiply this number by 9. Okay, so I'm going to use work done because it's a bit quicker. Work done is equal to the force of 15,000, and we multiply that by 9, and that will give you 135,000 joules. Okay, but we could have used this equation. We could have done 1500 times 10 times 9, and it would have still given us exactly the same answer. Okay, so the final part is about springs, and it's about stretching, compression, and we need to understand how deformation takes place. Now I'll put down here this keyword deformation, and that just means to change the shape of something. So if we change the shape of a spring, it could either be elastic, where it springs back to its original shape. So the word elastic means it will return to its original shape, like a elastic band or a spring. If you stretch it, it should return to its original shape. Inelastic deformation basically means if you overstretch it, it will deform, it will change shape, but it will never return to its original shape. So when you stretch a spring too far, it will never go back to its original length. Okay, so let's have a look at this. So the first thing we're looking at here is this spring has been stretched. So we call this stretching or extension. So we've stretched the spring. And in this case, we've pushed that way, so we have compressed it. So compressing a spring is when you make it smaller, and stretching it is when you extend the spring. Now let's go back to our original equations that we've learned before. We're going to talk about work done again. So imagine I apply a force on the spring to stretch it. So if I apply a 10 Newton force and I stretch it, say 2 meters, then the energy that I would have transferred to the spring is going to be 10 newtons times 2 meters. So that is going to be equal to 20 joules of energy. So what am I saying here? The work done, the energy I've had to put in stretching the spring is now going to be stored in the spring. So that 20 joules is going to be stored as elastic potential energy. I've used kinetic energy to stretch it, to move it, and now I've stored it. So I've gone from my kinetic store to my elastic potential store. I've got a new store of energy. Now I'm going to bring in a new equation here, and that is elastic potential energy. So the elastic potential energy is equal to a half, just like kinetic energy, times by the spring constant, which we're going to talk about in a second, and the extension squared. So I could work out the spring constant of any spring by using this equation if I know the energy. So we knew that our energy is 20 joules. That's how much energy is stored in the spring by stretching it, and that is going to be equal to 0.5. We're trying to figure out K, and that's times by our extension squared. Now we've just said we've stretched it 2 meters, so that is going to be 2 squared. Okay, so how are we going to work out K? Well, we know that if we are multiplying these things, the inverse operation is to divide. So we're going to divide by 0.5, and we're going to times that by 2 squared, which is 4. So I can now cancel that out and cancel that out, and 20 divided by 0.5 times by 4 is going to give me my K. So 20, 0.5 times by 4 is 2, and that is going to give me a spring constant of 10. Okay, and the spring constant, which we'll talk about later, is in newtons per meter. Okay, it's a capital N and a lowercase m. Okay, so moving on to the spring constant, we're going to talk about this more now with Hooke's law. So as you can see here, I've got the experiment that you did in your lessons, and we put a force of different, so 2 newtons, and we've got an extension, and then 4 newtons, and then 6 newtons, and then 8 newtons, and then 10, and so on. And you can see I've plotted a table here to describe that. And as you increase the force, you can see that the extension is increasing, and that's a relationship that we can draw on a graph is a directly proportional relationship. What does that mean? Well, if you remember that force is equal to the spring constant K times by the extension. Remember from earlier on in the video I said that if we increase one thing, the other must increase by the same amount. So what are we increasing? Well, we're changing the force. This is our independent variable, and we increase the force by 2, so we're doubling that. We must double this one as well. So that is our dependent variable. Now, if you remember, when we're drawing a graph, we should always put the dependent variable, the extension, here, and that is in meters. And we should always put our independent variable on the x-axis, which is our force, and that is in newtons. So by increasing the force, we are extending the spring, and this should give us a straight line. This should always start at the origin. You should always start 0 and 0. So a directly proportional relationship is a straight line that starts at the origin. It starts at 0 and 0. Okay, so let's look at some numbers, because we're going to use this graph now to explain the spring constant. So the spring constant is K, and K is just a relationship between these two things. So that means K is just a gradient. So K is the gradient of this line. The spring constant is the gradient of the relationship between force and extension. Now in maths, you should have learnt that the gradient of a line is equal to the change delta in y divided by the change delta in x. Okay? Now if we were to plot that, what that would mean would be our spring constant K would be equal to the change in y, this is y, and this is x. So it would be the change in y, which is our change in extension, divided by the change in force. Okay, now let's look at our equation. Our equation states that the force is equal to spring constant times E. So the spring constant K should be equal to F divided by E. Now you can see this equation contradicts what we've just talked about, and this is a problem with the exam. So really you should always plot the independent variable here and the dependent variable here, but in most exams they won't do that. The reason they don't do that is because if you then try and work out the gradient by the change in delta y divided by delta x, they're the wrong way around. Okay? So in your exam, they will probably put the extension on this x-axis, and they will probably put the force on this x-axis. That way, K will be the other way around, and when you plot this, you will have force divided by extension. Okay, so I'm just going to get rid of this ink, and then we're going to plot this graph. So we're going to look at working out K. So how do we do this? Well, when you're working out the gradient, you always take the largest value until it starts to curve. Now, if we remember from our Hooke's Law practical, this will be a straight line, and then at this point it will start to curve. We call this point here the limit of proportionality. That's when it stops being directly proportional. It's also called the limit of elasticity. They both mean the same thing. And we're going to use this value to work out our change in y divided by our change in x. Then remember, this is our gradient. Okay, so the largest value is going to be, if we have our straight line, remember, through the points, our largest value is going to be from this point to this point. So from there to there, we've got a difference here of 10. 0 to 10. So 10 minus 0 is equal to 10. So the difference is 10 newtons. On the other scale, on the y-axis scale, we've got a difference from 1.0 to 0. So 1.0 take away 0 is 1. Okay? Now I just said that really on the y-axis, instead of plotting the extension, you should really plot the force, because our relationship should be that the gradient should always be equal to the change. Remember, delta means the change in y divided by the change in x. Now, if we plotted this, they would be the wrong way around. So in an exam, it's highly likely that they're going to have a graph where you have, instead of the dependent variable on the y-axis, they're probably going to put the dependent variable there, and the dependent variable, sorry, they're probably going to put, the dependent variable there, which is the extension. Now this is wrong, but it helps with working out the gradient. Okay, the independent variable should go there, so the independent variable should be the force. Okay, now if we do that, we now know that the force is y on the y-axis and the extension is on the x-axis, so we can flip them around. So we now know that this fits our equation because force is equal to KE, so therefore K must be equal to F divided by E. And if we flip these around, we've now got that right. So you can see that delta Y is equal to F, like it should be, and that is equal to the extension. Okay, so for those of you who know this, what you could have done is you could have plotted a reciprocal of this graph. And remember, a reciprocal just means we flip these two around. So now we've got them correct, what we want to do is say that the force is this change. So the change in the force, remember, is 10 newtons, so we're going to put that as 10. And the change in the extension is 1. Now remember, you have to do the largest change. Okay, the largest change is going to give you an accurate result, an accurate gradient. 10 divided by 1 is equal to 10. And remember, the units, force is in newtons, extension is in meters, so therefore this is going to be in newtons divided by meters, newtons per meter. So our spring constant is 10 newtons per meter. And this is how we work out the spring constant and what the spring constant actually means. It's basically telling you how much effort you're going to have to put in to stretch a spring. So it's related to the extension and the force. So the greater the force, the greater the extension. That's all the spring constant basically means. Okay, so that is a directly proportional relationship. We're now going to have a look at inversely proportional relationships. So for this one, I'm going to talk about another thing you need to learn in another video, which is frequency and time period. So you may remember that frequency is equal to 1 divided by the time period. Therefore, if we swap those two, we would know that the time period is also equal to 1 divided by the frequency. Okay, so what does this mean? Well, remember I said that if you have a relationship like force is equal to KE, we would say that that is directly proportional, because if I increase the force by 2, I would increase the extension by the same amount. They are directly proportional. Increasing one by one value will increase this by exactly the same amount. If I double the force, I double the extension. Well, inversely proportional is the opposite of that. If I increase T by 2, what will I do to F? Well, let's have a look at some maths to help us understand this. So if I say that the frequency is equal to 10, and that is equal to 20 divided by 2, okay, just to use a bit of maths to help with this, if I increase 2 and I double it, I increase it by 2, what am I doing to this number here? Well, let's do 20 divided by 2. 20 divided by 2 is equal to 10. So if I do 20 divided by 2 and I times that by 2, I've now got 20 divided by 4. Can you see that 20 divided by 4 is equal to 5? So by increasing this number by 2, I decrease this number by 2. So inversely proportional basically means that when you increase one variable by 2, you must decrease the other by 2. The exact opposite would happen with t. If I increase t by 2, then I must decrease f by 2. So they are inversely proportional. Directly proportional means that when you increase one by 2, you increase the other by 2, or if you increase one by 4, you increase the other by 4. They are proportional to each other. This one, when you increase one by a given factor, you must decrease the other by a given factor. And this gives us a relationship which would look like this on a graph. So you can see they are inversely proportional to each other, and we would get a curve. So an inversely proportional relationship looks like this, and it's kind of like a half-life graph. Okay, so that's the kind of graph that is inversely proportional, and remember, directly proportional would give you a straight line that always begins at the origin. Okay, so that covers springs, and it also covers directly and inversely proportional relationships. Now, to practice this, you need to have a go at all the exam questions related to forces.